Hello. So in this session, we will solve a wave equation of finite string. Okay. See, there are wave equations with infinite string given, so that we will solve later. But first, we will solve wave equation with finite string. Okay. And here we have three types of wave equation. So we will cover all the types. So first, let me categorize them. Okay. So I'll fit them into three types. So type one is the du upon del t square equals to c square del square u on del x square. Now degree of this equation is here 2 and here 2. Fine. So basically we need here four boundary conditions. Four conditions. Okay. Initial and initial and boundary conditions combined together should give you 4. Okay. So let me impose the conditions here. So that means u at the initial, it will be 0, and u at the final end will also be 0. So I say length is L, that is 0. And now I'll impose the one condition under ux0 equals to f of x, and all this condition will remain in the picture equal to 0. I'll keep this thing 0. Okay. Now let me explain all the factors which are involved here. Okay. Last it was heat equation, now it is wave equation. So even in wave, this x will now play the role of, I'm sorry, there's no x. Once again, I made a mistake. This heat equation is not flowing out of my mind. So it's wave now. Okay. Yep. So t is as usual, it's time. Okay. So the only thing is that here t must be greater than 0, and since this is for finite length, so basically we will get this 0 less than x and less than some L. Okay. That's the length of the string. Okay. And now the solution that we obtain uxt is nothing but the disturbance basically. Okay, it's nothing but the disturbance in the string or system. Okay, in the string or the system. Okay, geometrically speaking, then just consider a string of length L. Okay, string of length L here. Fine. Now it's of length L, so this part is here L, this is 0, and now I'm saying that disturbance at this end is 0. So that's how we got this condition, and disturbance at the final point, this is again 0. And in between it, there is a disturbance that will give rise to a function which is my f of x. Okay. So I have to check the behavior, uxt, how it performs. Okay. So that's how our type 1 is. Okay. For the wave equation. Okay. So now similarly, I'll impose one more function here. So it will be again g of x something, and then I'll get different types. So basically in this type, first let me write down the solution for this type. And as I have told you that I'll be deriving the proofs for each and every type. Okay, after the end of this section, in fact, not session. Okay, after I complete this heat, wave, and Laplace, I'll derive the equation for each and everything. Fine, but for the time, we will just consider its solution and then try to solve all the problems from CSIR NET, GATE, and other exams. Okay, so let me change the page first. Yeah, before that, we should consider this thing also. Okay, so the solution is given by solution. Let me write down here only. Okay, the new ink. Okay, so its solution is given by okay, u of x t equal to summation of dn into sine n pi x upon L into cos n pi c by L. What is not writing? Yeah, cos n pi c upon L into times to t. Fine. So this is the solution of a wave equation. And now let me write down what is this dn. So dn here is again same thing. Okay, that earlier we used to find out by using Fourier sine series or Fourier cosine series. Okay, so here in this case it will be 2 upon L, the similar that we had found earlier. Okay, the same thing will again come here also. So it's 2 by L and integral 0 to L f of x into sine n pi x upon L dx. Okay. So the solution for this type of wave equation is given by this quantity. Okay, dn times sine n pi x upon L into cos n pi c upon L t, where dn is this quantity 2 upon L integral 0 to L f of x into sine n pi x upon L dx. Okay, this is for type 1. Okay, so whenever you get a problem, first you have to recognize in which type it fits. Okay, suppose it gets into type 1, then you have to apply this solution, and if it gets into type 2, then you apply the solution for type 2, and then similarly for type 3. Okay, and if you do not find all these boundary conditions mentioned, and this string is not finite, then it will be basically infinite length string problem that we will solve using a Lambert solution. Okay, that I'll mention after the in my next video. Okay, the Lambert solution. Okay, this was for type 1. Okay, now let's discuss type 2. Okay, so type 2 here. Okay, it's for type 2. Same thing, everything will remain same, only this boundary conditions will change. So it's del square u upon del t square equal to c square del square u upon del x square, and let me impose the boundary conditions. Okay, and impose the boundary conditions, then I'm getting this u of 0t is 0, and at the final ult is also 0 now, and this time I'll keep ux0 to be 0, while this quantity, okay, ut of x comma 0 equal to some g of x. Okay, earlier it was switched, there it was 0 and this quantity was f of x. Now I got a new one, so basically I'll impose this condition. Okay, so this is another type of problem. Okay, and now rest everything will remain same. Okay, t is time there and uxt is nothing but the disturbance. Only thing that will change is its solution. Okay, and solution is not changed by a significant factor. Okay, it will just changed by a simple thing. Okay, rest of the things will remain same. Okay, so let me write down the solution. Okay, so solution of this type is given by, okay, solution of this type is given by u x t equal to summation n equal to 1 to infinity. Earlier I had written dn, but this time I'll write down en just for the simplicity, nothing else. Okay, so that don't get confused. Now it's sine of, okay, n pi x upon L into sine of n pi c upon L t. When derivative was 0, so we got their cos, and when derivative has a function, okay, some g of x, then we again get sine. Okay, that's the strategy involved here. And now let me write down what is this en. So en still remains same. Okay, as long as there it is sign here, en and dn will not make any difference. So en is here, same thing, it's 2 upon L times integral 0 to L, and then g of x into sine n pi x upon L dx. Okay, so that's the solution for type 2. Rest of the things will remain same. Okay, there is no difference. And now we'll see type 3. Okay, on the same page. Okay, let's see how type 3 looks. So basically now users must be getting the idea. These two conditions are fixed, okay, everywhere, only these two are changing. So earlier I had kept ux0 equal to f of x and utx was 0, utx comma 0 was 0, and now this time I got this ux0 equal to 0 and utx0 equal to some g of x. Now in type 3 I'll just impose conditions on both of them. In fact, u of x0 will be a function and utx comma 0 is also a function. Okay, so that will make us contribute our type 3. and solution will be nothing but their addition. Okay, I mean addition of type 1 and addition of type 2. Okay, so that will be the solution for this type 3. Okay, so let me write down the type 3. Okay, it's better to be on a new page, in fact. Okay, that will make a good impact. So type 3, okay, del square u upon del t square will be equal to c square times del square u upon del x square. Okay, and 0 less than x less than L and t is greater than 0. Fine. Now let me impose the boundary conditions. These are initials ones. So 0 2, it's 0, and u L t is also 0. Well, this part will give me a headache now. U x0 will be my f of x, and u t x0 will be my g of x. Okay, and now their solution. Okay, so their solution is nothing but, okay, so the solution is given by be very careful while writing the solution. Okay, it's nothing but the addition of these previous two solutions. Okay, so let us add them. First we had n equal to 1 to infinity dn sine n pi x upon L into cos n pi c upon L into t, and plus summation of n equal to 1 to infinity, the solution that we obtained in type 2. It was sine n pi x upon L into sine n pi c upon L. Okay, now just combine them, in fact, because we see that this part is appearing both in both the terms. Okay, and the series starts from the same quantity, so I can just club them and write down n equal to 1 to infinity. It will be basically dn cos n pi c upon L t plus en sine n pi c upon L, and this quantity will come out sine n pi x upon L. Okay, and this dn and en are still same. Okay, while en will make a little difference here. Okay, and give me a chance to correct my mistake here, because I think I made a mistake. Okay, just now I recalled. Here I think en is not that simple. Let us in fact derive the solution from this solution only. Okay, uxt, what it will be. So we got uxt in type 2 as this quantity. Fine. Now I do not know what is this en. Okay, because I don't consider this thing to be correct. Okay, because just now when I was writing this solution for type 3, then I recall that if dn and en are same basically, then I can take even them out, but that is not possible. Okay, so let me derive the expression for this en quantity. For the time I'll just erase this. Okay, make a correction here. This is not correct, so I'll ignore it. Now let us differentiate them just to apply this condition. Okay, so I'll differentiate this entire series. So since this series is basically convergent, so it can be differentiated term by term. Now I'll differentiate them with respect to t. Okay, so rest of the things will remain same here. N equal to 1 to infinity en, and this sign term will not be affected because the derivative is with respect to t. So it will be cos n pi c upon L t, and again I have to take the derivative of this thing. Okay, so this will be just n pi c upon L. Okay, so this part will come extra, and now let me put 0. So basically I'm getting ut of x0 will give me summation n equal to 1 to infinity en, and I think this is a constant, so I'll write down outside. So n pi c upon L. Okay, wait a second, no, I cannot do that even, because even this is not allowed because n is inside the picture, so we cannot take it outside. Okay, so let's write down here only. So n pi x upon L into, and when I put here 0, then this cos 0 will give me 1. I'll be just left with n pi c upon L. And now if you compare this series, then this appears to be Fourier sine series, where this coefficient will now be equal to the, that means this coefficient I'm equating, and the rest of the thing is a Fourier sine series. So where this now En and then n pi c upon L will be equal to 2 upon L integral 0 to L f of x into sine n pi x upon L dx. Okay, so now I can just cancel out this little L and I get now En. Yeah, that will be my final expression. So En will be equal to, this 2 will come down, so 2 upon n pi c times integral 0 to L f of x into sine n pi x upon L dx. Okay, so that's the expression for my En in this solution. Okay, so solution is given by star, and where En is this quantity. Okay, please make a note of this thing. Okay. This was lagging. Okay, so in case you forget what is your En and Dn, you can simply derive this by the given conditions. Okay, it's that simple. While I'll be deriving the proof, so you people will get the better idea, in fact, how to go for it. Because obtaining this solution is not easy, but we will apply a variable separable form to obtain the solution. Okay, and when solution is obtained, then there is no harm in finding En and Dn, these things. You can simply apply your boundary conditions and to obtain your Fourier coefficients. Okay, now let me write down this Dn and En here again once again. So what is Dn basically? Dn was perfect. Okay, it was nothing but 2 upon L integral 0 to L f of x into sine n pi x upon L dx, while En was a little different. Okay, while En was nothing but 2 upon n pi c times integral 0 to L f of x into sine n pi x upon L dx. Okay, so we are now ready with 3 types. Okay, now I'll be taking few problems from various exams, and that we will see in which category it belongs. First we will compare them, and then we will see accordingly which solution we must apply. Okay, either from type 1 or type 2 or type 3. And nowadays mostly they will ask you infinite string problem, because that requires solving by D'Alembert's method. Okay, and that's a little tricky because it involves a second order integral and first order integral and then all these two terms that will be followed later. Once we complete this these things, I'll upload one more. Okay, that covers your D'Alembert solution. Okay, so let me consider the problem. And if you notice, then in this part in type 2, this everywhere it is g of x. Okay, and we are using here f of x for no reason, so make a correction there even. Okay, this is just g. Okay, not a big mistake. This is just g. Okay, I'm using different notations so that this looks familiar to you. Otherwise, because standard practice is to take ux0 equal to f of x. This is here is f of x, and this quantity with derivative we take it g. So you should not be confused. So that's why whenever I'm writing g, that simply means it is for type 2. Okay, whenever derivative is at t and there is a function, that means it is for type 2. And whenever I'm writing f, that means it is for type 1. Okay, in type 1, see, we have here f of x. Okay, that's what I'm talking about. Everywhere we are using f of x. Okay, so in type 2 we are using g here. Okay, so in type 3 in this En part will get changed to just g of x. Okay, now let me consider a problem. Okay, so that you understand it better. Okay, so now look at this problem. Okay, it's again a wave equation with 4 conditions here. Okay, so first condition that disturbance at both the ends are 0, and ux0 is since it is at x0 and this is derivative free, so this part will be our f of x. Okay, and this is 0 here, so our g of x is 0. Okay, so that means it is simply our type 1 problem. Okay, that we have covered. Here it was ut of x comma 0 equal to 0. So basically you should recognize the type first. Okay, and now we see that this is type 1 problem, so its solution is given by uxt equal to summation n equal to 1 to infinity, okay, dn into sine n pi x upon L into cos n pi c upon L t. Okay, this t is not separate because it's with cos only. I'm writing outside the bracket because I feel that it's n pi x upon L, so it's n pi c upon L. There should be no confusion between them. Otherwise, if I just mention t inside, then I get confused in fact. So that's why I write t outside. It varies from person to person. Cannot avoid. Now, and this dn was nothing but 2 upon L, an integral 0 to L. Now it is f of x. So f of x times this entire quantity with, that we have obtained using the Fourier sine series only. Okay. Now, so let's compare with this thing. Okay, with the standard heat problem. So what we get. Okay. So comparing with standard heat problem. I'm sorry, wave problem. Comparing with standard wave problem of type 1. Standard wave problem. Okay. Of type 1. We get c equal to 1 because here there is nothing, so c is 1, and your f of x is nothing but sine cube n, oh not n, just x pi by 2. Okay, x pi by 2. Okay, so that's my f of x. Now let's find out this dn first, because once we find this dn, rest of the things will automatically follow. Okay, so dn in this case will be, and one more thing, length is 2. Okay, here length is 2. This part will give you length. In fact, if it is not given, then it starts from 0 and ends at 2. So length must be 2. Okay, 2 minus 0, nothing else. Okay. So dn will be nothing but 2 upon 2 will get cancelled. So, but still I write down because that will help you. And f of x is sine cube pi x by 2 times sine n pi x upon 2 then dx. Okay, so our goal is to calculate this integral. Okay, so let me consider this on a new page. So dn will be equal to integral 0 to L sine cube pi x by 2 times sine of pi x by 2, which is n pi, and then dx. This L was also 2, so rather than writing the entire thing again, write down t2. Okay, now we have to integrate this, and now I just want to get rid of this factor because it is causing me a lot of trouble, pi x by 2, and even it is here pi x by 2. So I'll put this quantity at something. Okay, so I'll put pi x by 2 equal to some, let me not write down t because t is into the picture, so let me take some other variable, let's say z. Okay, now let's change the limits. So as x equal to 0, your z will be 0, and as x equal to 2, z will become pi. Now let us differentiate them at the same place. So you get dx equal to 2 upon pi dz. Okay, so my dn will now become integral, this was 0 to 2, so now it will become 0 to pi, 0 to pi sine cube z into sine n z, and dx is nothing but 2 upon pi. So 2 upon pi I'll write down outside. Okay, and now we have to get rid of the sine cube z. So we have a formula, okay, from our lower standard that we have been following. Okay, it's nothing but sine 3 theta equal to 3 sine theta minus 4 sine cube theta. This quantity right here should give us sine cube theta from this. So I get basically 4 sine cube theta equal to 3 sine theta minus sine 3 theta. So I need here just sine cube theta, so I'll divide by 4. So I'm getting 2 upon pi, then integral 0 to pi, and the sine cube z part will become 3 sine z minus sine 3z upon 4 times sine of n z dz. Okay, and now I'll simply separate the terms. So basically I'm getting, now I'll be multiplying this. So 2 upon pi times integral 0 to pi, and this 3 upon 4, and then sine z into sine n z dz minus 2 upon pi, then integral 0 to pi 1 upon 4 times sine 3z into sine n z dz. Okay, so I think this formula looks familiar. 0 to pi sine mx into sine nx. Okay, we have already seen that this is your dn. So this exists only, I mean this becomes 0 when they are not equal. So here it is just sine 1z, and here you have sine nz. Okay, so it will be true only when I have n equal to 1. So that means only d1 will exist, and this thing will 0. And when d3 exists, okay, when n equal to 3, this quantity will become pi by 2. And then when d3 exists, then this quantity will become 0 because they will not be equal. Okay, so we will basically get d1 first. Okay, so let's find out d1. So d1 will be 2 by pi, and this 3 by 4 will be also outside, and this entire quantity will become here pi by 2. So that will give you 3 by 4. This part will become 0 for d1 because here I'll get sine z, and here I have sine 3z. So that will give me 0. And similarly, when I go to find out d3, in d3 this quantity will become 0 because I'll get here sine 3z into sine z. So that will become 0. And d3 part will give me minus 2 by pi. Then 1 upon 4 will be here. And then integration of sine 3z into sine 3z in 0 to pi will be nothing but pi by 2. So I'll get this part getting cancelled with this and giving me minus 1 by 4. So I got d1 and d3. Okay, d1 and d3, where d1 is 3 by 4 and d3 is minus 1 by 4. Okay, now let me write down the solution. Okay, so solution is given by uxt equal to summation n equal to 1 to infinity dn sine n pi x upon L into cos n pi c upon L into t. Okay, now we know that this L is 2, okay, and the C is 1. So let me open this bracket first, and that will give me d1, and then sine n pi x by 2 into cos n pi t by 2 plus d2 sine n pi, oh I'm sorry, when it is n, then why I'm writing this n? Okay, this n will not come now because we have opened the bracket. So it will be basically 2 pi x by 2 into cos 2 pi c is 1, and this by 2 t. And similarly we have here d3. So d3 is sine 3 pi x by 2 into cos 3 pi t by 2. And we have seen that this only d1 and d3 will exist, and rest of dn equal to 0. Fine, rest of dn's are 0. So basically I only this term will survive, this first one and this third one. this term will become 0. So just plug in the values. So d1 is 3 by 4 times sine pi x by 2 into cos, okay, it is again here n only, so cos pi t by 2. Let me replace this n by 1, okay, because we have opened the brackets. And d3 is minus 1 by 4, so minus 1 upon 4 into sine 3 pi x by 2 into cos of 3 pi t by 2. Okay, so that's my required solution. Okay, so this problem is now solved. See you in the next problem. Thanks for watching.